Okay, we're going to go into another sort of item that we wanted to cover today, and it is this idea of dependent motion. So sometimes you have bodies that move at the same time. They might be linked mechanically in some way. You have one body that's moving, you have another body that's moving. When they're linked mechanically, you can actually relate the motion of one to the motion of the other. Okay? When you are doing this, there's kind of a set of steps that we can go through in order to sort of set up the math that helps us to do these descriptions of motion. So the first one that's recommended here is you find kind of a few points in the mechanism that are moving that might seem like they are key points, right? The next thing you have to do is establish usually fixed locations that kind of establish the relative to which those points, those key points that we just talked about, are moving. So it's kind of, they're moving relative to what? And you establish a fixed line that they are moving relative to. That won't necessarily make a whole lot of sense until I do an example. So we'll just say that's kind of the next step, is establish some datums. The next thing is to establish variables that describe those key points' positions in space, and you do that relative to the datums, right? So you have, what is the position of this key point relative to this fixed location? The next thing you have to do is write the actual equation or equations to relate the positions. And then lastly, once you have that equation for position of one piece versus another, you can take time derivatives in order to find relative velocities or accelerations, or you can find the velocity or acceleration of one body in terms of the other. Okay? So this is kind of what we're going to do, and we're going to do it on this problem. Okay? Pulley problems are classic dependent motion problems. It's not the only thing that creates a dependent motion problem, but this is certainly a category that can create dependent motion problems. Okay? So for this problem, we know that block A moves according to this function. So let's say that this function that we are given here is actually the acceleration of block A relative to time. Okay. We are also given what the initial velocity at time 0. We're given what the velocity of block A is. Okay. And we're going to define all of the motion relative to its current position right now, right? Which we actually don't necessarily care what exactly that position is, which is why we're defining relative to this. It's not really the point. You don't have to know that in order to know relative velocity, relative position, or relative acceleration of blocks A and B. Okay? So for this, what we want to do is, first of all, find functions for velocity and displacement of block A. And once we have those functions, we want to find what the values of those functions actually are when t is equal to 3 seconds. Okay? So this is, at the very beginning I mentioned that there's sort of two big types of these problems. One is ones where you pick off at this instant what's going on, and then another one is here's a function that describes more of time and like more of the motion, and then it's up to you to figure out how did the motion ensue so that you can determine things like position and velocity at any time, right? And that's more of this style of problem. And to kind of give us a little bit more concrete and output, I'm saying pick off one time, let's say 3 seconds, and we can find it at that time. But you could also find it at other times if that's something you wanted to do. Okay. Part B, I want us to find functions for velocity and displacement and acceleration of point B. Okay. I want that in vector form, and I want those values at time equal 3 seconds. Lastly, I want functions for the acceleration, velocity, and displacement of block B relative to block A. Okay, and then the magnitude of that vector, again, at 3 seconds. Okay, so far so good? what should we do first? I'll tell you what. The first part of this problem is review. Okay? The first part of this problem is just a linear motion problem, right? Because you are given acceleration for block A. That acceleration function can be manipulated in order to find velocity and displacement. So we're going to start with that. Part A, okay, we'll say finding v of A as a function of t and the acceleration of A as a function of t. All right, not A, excuse me. What was I trying to find? Okay, we're trying to find displacement, right? And I'll just call that R sub A. All right, so what do I need to do if I know acceleration and as a function of time, and I want to determine velocity as a function of time? Okay, this is my acceleration as a function of time. I can bring it down here. What do I do to it? Velocity of A as a function of time is going to be equal to an integral. To go from acceleration to velocity, we have to integrate. Okay, we integrate from 0 to whatever time t we want to stop at of all of this stuff dt. All right. This isn't quite enough, though, because we also need to add on whatever our initial velocity is. Okay, our initial velocity happens to be 2 inches per second. All right, doing this integral yields what? We'll do it term by term here. So remember, to take an integral of a polynomial like this, you can go term by term. If you have a variable to a power, you can take that power and increase it. Okay. Then what? Divide by the new exponent, right? And so if you divide by the new exponent there, it ends up giving you 2 inches per second to the 4th. Okay, then what? Minus, here I can take that t, take it, increase the exponent there, divide by the new exponent, and it ends up giving me 5 inches per second cubed. Okay, for the last one, okay, I basically have t to the 0, right? If you have no t there, that means t to the 0. So you increase that by 1, and that gives you t, and divide by the new exponent. That new exponent's just 1, so I just leave the 4 inches per second squared. Okay, and of course onto all of this I add 2 inches per second. All right. When you want to know what this is at a particular time, all you have to do is you plug in 3 into t. Okay, so I'll say plugging in t equal 3 seconds. VA at t, or of t, turns out to be, I'll say, instead of putting t here, let me put, 3 seconds. Okay, that ends up giving me -1 inch per second. And if I want to express this as a vector, like v vector a, right, at 3 seconds, what direction is it going? Okay, based on what you see on here, what direction does it look like body A is going to move in this situation? Okay. I would say it looks like it's a vertical movement, right? So I can put on here that this is going to be equal to -1 inch per second j, given the x and y coordinate system that I identified up there. Okay, so that's a function for the velocity of block A and the value of it at time equal 3 seconds. Okay, there's that, there's the function. Okay, what about the position? The displacement. All right, well, we do the same thing again, right? We integrate. My computer's getting slower and slower. So, I hope we make it. All right, we've got all of this stuff. We're going to integrate it from 0 to t dt. Okay. Do I need to add an initial position? Okay, I mentioned this a few seconds ago. I don't need to add an initial position because I'm assuming my initial position doesn't really matter. So we're just going to say whatever position it's in right now, that's the initial position. We'll call it 0. You know, whatever it's in right now, we'll call that 0. Okay, so when I take this integral, what does that look like? Okay, again, we take the exponent here and raise it by 1. That gives me t to the 4th. Okay, I'd bring that, divide by that new exponent, and that ends up giving me 0.5 out here. Inches per second to the 4th. Okay, the next one, I increase that exponent by 1, which gives me t cubed. Take that new exponent, divide by it. Okay, then I have t. Again, I increase that exponent, which gives me 2. 4 divided by 2 is 2. Okay. Lastly, I have t to the 0 is the original power of the t that I have in this 2 inches per second. So that means I increase that by 1 and I get t. Divide by the new exponent. And that's what I've got there. All right. So this is the function that I have for r. Okay, again, I can plug in t equal 3 seconds. And when I do that, we can say that the displacement that it goes to is 3 seconds. The displacement it goes to is negative 16.5. and this is not inches per second, right? This is just inches. Okay. How would I find my acceleration for part A at 3 seconds? What would you say? That's like super easy, right? Super easy because I can take that original function and I just plug it in, right? Take this function, which is the function for a of a, right, the acceleration of part A as a function of t, was all this stuff. If you plug in t equal 3 seconds, what do you get? This one I don't have done already, so I need to go back to here. Let's see. I got 6 times 3 squared minus 10 times 3 minus 4. So I've got 20. That would be in units of inches per second squared. Okay, and what we're really saying there is that 3 seconds after the thing begins motion with this acceleration function that's given, right? 3 seconds after it begins motion, it is now accelerating at 20 inches per second squared, meaning it's picking up speed, and in what direction? It turns out to be a positive number here, right? So what does that mean in terms of direction? It's picking up speed going up, right? The velocity is actually negative still, right? Even though we've started to pick up speed going upward, right? Really what we're doing is we're slowing down how fast it might be going down. We're slowing that down, and at some point it will reverse direction and start going back up, right? So it's a good idea to always sort of get keep a hold of the physical meaning of velocity, acceleration, and position, right? So I very frequently will do that once I calculate these things. I think about what is this acceleration? What is a velocity? What is a position, right? All right, so there's all of part A and more, because I don't know if I even asked for the acceleration at time 3 equals seconds, or time equal 3 seconds. All right, shall we move to part B? Well, we sure will. And it will be fun. Isn't it great when people are chipper and you're not? And you're kind of like, shut up. This is not fun. We're in school in the summertime. Yes, sir.
I'm kind of having difficulties visualizing what's happening.
Okay. So what we just figured out, we are given an acceleration for block A. We're given a function that describes acceleration of block A in terms of time. If you know acceleration of block A in terms of time, you can get to the velocity of block A in terms of time by integration, right? That's what we did first. So basically we wanted a function that gave us what is the velocity of block A as a function of time, right? We did that by doing this first integration. And so what we came up with is a function that gives that to us as a function of time. I'll tell you what we can do here, actually.
So block B is the pulley moving?
Block B, yeah, so I have these labels A and B, right? So this is part A right here that would move up and down. It's kind of the big pulley right there, right? And then the thing block that's built onto it. B is up here on this incline, right, moving along that incline direction. Okay? So what we've just done is we've figured out velocity and position functions as a function of time in each case for block A. All right? All right. This next part is really sort of the real crux of this problem, all right? This goes into the dependent motion stuff that I was talking about just a second ago, all right? And to really do this, what I'm going to do is actually copy this figure. I don't really need to copy it. I'll just write right on it, okay? We need to establish some things. When you have ropes like this, one of the easiest ways to think about the ropes is to define enough dimensions on the system so that you can fully define the length of the rope. All right? And so what I'm going to do is define a few of these things. First of all, I identify, actually, if we go in the same steps as I identified right at the beginning, find the points we care about that move, right? We can actually go in that order and figure that out first. What points on this thing that move do you think we care about? Okay. Let me say, it looks to me like point A is certainly one that moves that I care about, right? And so what I'm going to do, kind of helped us out a little bit by showing this fixed surface down here. Now this pulley can kind of ride up and down in between that fixed surface, but it gives me a nice physical thing that I can identify and say, this is my datum, right? And I can identify that I measure up to the point A, and I'm going to call that R sub A, right? As that changes, that describes what is the height of that point A, right? And that's a point that I care about with respect to the motion of this system, okay? What's another point you think I might care about with this system? You feel like point B might matter? Okay. So I think that too. And so what I'll do is I'll define another datum. This one's not sort of already set up for us, but let me define a datum relative to which I can describe the position of this point B. Okay, so I'm going up to that point right there, and I'm saying that you know, what I just drew right there, let me call that RB. Okay. So those are a couple of things that we might care about. What else do you think we might care about? How about the height of point C? All right. That seems like that might be something we might want to define in terms of a variable. All right, but we still don't have enough stuff here to actually fully define the length of each of the ropes. All right, and just to kind of be clear here, we're dealing with how many ropes? How many ropes do you see on there? 2 ropes, okay? I'm going to label them up here. We'll call this one rope 1. And down here, this one is rope 2. All right. I need to define a few other lengths to really define all of the lengths of all of this rope. Let me show you one of them that I'll show on here. Let's say that it from this datum that I have right here up to this location right here. I'm going to call that L. Okay, and that's kind of, imagine all of this is at the same position right here. Okay, let me also define how far it is from this datum down here up to this height up here. I'm going to call this, we'll call this H2. I'm going to call this other height over here H1 up to this point. Okay, and I'm kind of missing one more dimension that I can define here, and that is how far is it from this pulley to this pulley. Okay, W. Now you might say, well, there's a few things you're ignoring in terms of the length of the rope. The rope takes some length to go around certain pulleys, right? To give you a little preview, ultimately anything that ends up constant in this system, where once we take derivatives, everything that's constant, what happens to it? They go out, right? The only things that matter are the things that might have movement associated with them, which means that the derivative would not go away if they had movement associated with them. So that means all the rope that's wrapped around the pulleys ends up not mattering. Okay, so we're going to actually express this length minus the length that goes around the pulleys, because that, unless I gave you information about the diameters of the pulleys, you wouldn't be able to get those. I could do that. It would just really complicate the problem and for no reason. Okay, at least not for our purposes. All right, so we've got all that stuff on there. What I want to do is actually write some functions that describe the length of these ropes. And we'll start with rope number 1. Okay, and we'll say that rope number 1, we'll just call this length 1. Length 1 is going to be equal to, all right, the first one that we'll look at is how far is it up here from B back to where the rope goes around that pulley. How far is that? Well, in terms of our variables, it will be L minus R sub B, right? How much rope do I have there? Well, I have 2 of those, right? So I have rope that comes up along here, and then another rope that goes up along there, right? So I have 2 lengths that are L minus R sub B. So I'm going to say 2 times L minus R sub B. All right, what else do I have? Plus W, okay, plus what? And we'll count the kind of the length of this little attachment thing C right here as well. We'll count the length of that. So what we'll have there is H2 minus R sub C. Right? Anything else? Okay, that looks kind of like it's it to me. All right. Rope 2. Okay, the length of rope 2 kind of add up this stuff. First of all, we have R sub B. All right. Then we have, what's our length here? Looks like it'll be H1 minus R sub A. All right, so plus H1 minus R sub A. Then what? Okay, the little segment. So far I did this segment first. I then did this segment right here. How do I get this segment over here? close. I would actually say r sub c minus r sub a, right? So I would say r sub c minus r sub a. Okay, and then lastly, how do I get the last segment that comes down right here? Another r sub c. All right. Now here's the thing. Nothing in this question asks about the motion of pulley C, right? We're mostly, it looks like, focusing on the relationship between the motion of A and the motion of B. So if I was to eliminate variable r sub c, which describes the position of C, that's okay with me, right? I don't need to know that one. That's not one of the things that's being asked. It's something I could go back and find later if I wanted to, but for what's being asked, I can get rid of r sub c. To do that, let me actually take this expression right here and solve it for r sub c. Okay, so if I solve this for r sub c, it gives me that r sub c is going to be equal to 2, I'll go ahead and expand this out, 2L minus 2RB plus W plus H2, okay, minus length. And then I'll solve this one for r sub c as well. Okay, this is just a little bit different, right? But I can solve this one also for r sub c. To do that, I can end up with 2 times r sub c, right? Because there's 2 instances of it there. 2 times r sub c. I'll keep that on this side of the expression. It's going to be equal to length 2. Okay, minus r sub b minus h1 plus r sub a. Okay, got my r sub c's collected, plus another r sub a. All right. So now that I've got all this, what can I do? How about this? Why don't I divide both sides of this by 2? So now what? I know r sub c in this equation and r sub c in this equation. I've got them both solved. I can equate the 2. So that gives me that 2L minus 2RB plus W plus H2 minus length 1 is equal to length 2 minus R sub B minus H1 plus 2RA, all of this over 2. All right, so that means I can go over here and say this ends up being 4L minus 4R sub B plus 2W plus 2H2 minus 2 length is equal to length 2 minus R sub B minus H1 plus 2R sub A. And ultimately what I'm trying to do is express RB in terms of RA, right? So if I want RB to get part B of this problem done, I need to express it in terms of RA that I just did all this work to find these functions for, right? If I can get one expressed in terms of the other, then I'm good to go. All right, so I need to solve for RB. All right, so if I add RB to both sides of this expression, it ends up giving me 3RB on the left side. Would you agree with that? If I add the RB that I have over here to the 4RB that I have over there, it actually ends up giving me not 3, but -3, because I'm adding 1, it ends up giving me -3 like this. And this is going to be equal to length 2 okay, minus h1 plus 2r sub a, okay, minus 4l minus 2w minus 2h2 plus 2 length 1 and I divide through by -3. Okay, so if I divide through by -3, I'll do that term by term. All right, so RB ends up being, okay, negative length 2 over 3 plus h1 over 3. Okay, here we have minus (2 over 3) RA plus 4L over 3, okay, plus 2W over 3 plus 2H2 over 3 minus 2 over 3 times length 1. All right, and finally we're there to where we can say what we want to do is take a time derivative of both sides of this function, right? d dt on this side is equal to d dt of this side. All right, now what happens? Is length 2 constant? Length 2 is constant, h1 is constant, L is constant, W is constant, h2 is constant, and length 1 is constant. So we went through all of that. I intentionally, wrote out the whole thing, because once you get to the point where you take a derivative, a lot of these things go away. And it tells you here that r dot b, which is equal to the velocity of b in the direction that it's traveling, okay, is going to be equal to, okay, 2/3 are just constant, so it's going to be equal to minus 2/3 of RA dot, which is equal to minus 2/3 of the velocity of A. So, to kind of put a point on this, so let's see, I'll go ahead and state it this way. VB is going to be equal to minus 2/3 VA. Okay, can I do another derivative? Okay, when you look at this, is there any reason I can't take a derivative again with respect to time? And the answer is no. And if I took another derivative with respect to time, I find that the acceleration of b is going to be equal to minus 2/3 times the acceleration of a. Okay, well, why is this important? Glad you asked. What I'd like to do is actually finish this problem up in Mathcad, because the rest of it, after we get this relationship of negative 2/3, the rest of it is a lot of pretty much just plugging and chugging. And there's not a lot of thinking necessarily that you got to do from that point on. And so to get fast results, what we'll do is we'll start plugging that stuff into Mathcad. All right, here's my Mathcad sheet that I've already gotten started with. In case you aren't familiar with how to do some of these things in Mathcad, let me just touch on them real quick before we get into the next part of the problem. I first defined the acceleration function, and because I'm doing these problems here where I'd like to use these, they're called symbolic manipulations that you certainly can do within Mathcad. Even though it technically can do these with units, I find that units a lot of times get the kind of the algebra engine that's behind the scenes. It gets it confused. And so if it's possible for you to set this up to where you are not dealing with units within the expressions, it makes it easier. And so what you'll see here is I have this acceleration function defined and evaluating it at 3 seconds as the question asked me to do, and that gives me the same result that I got doing it by hand just a few seconds ago. You'll notice here I put in I put that function in manually. One of the things I want to show you here is that you don't have to put that in manually. You can go in here and actually put this in as the name of that function as a function of t evaluated from 0 to t, and it ends up giving you, it may end up in a different order, but it ends up giving you something that's equivalent to what you had gotten before. Where I define my velocity function next down here, you'll remember I had that initial velocity that I had to include there. So my point with this is not to kind of redo all this stuff. My point is that it's actually very easy to get Mathcad to do your symbolic integrals and derivatives in addition to other symbolic manipulations, if that's something that you might want to use it to check yourself. I wouldn't use it as a complete replacement of having to do some of those derivatives and integrals, but you can use it to check your work. You'll also notice here, while I have these functions defined, I may as well plot them. And so this is what the acceleration, the red curve that you have right here, is the acceleration in that time between 0 and 3 seconds. And you'll notice there it starts out negative and goes even more negative before it starts curving upward. Right around the 2-second mark, it crosses to being positive acceleration. And you'll notice there that where the acceleration starts to go positive, this next curve, the blue curve, which is velocity, stops declining and starts inclining again, right? So that makes sense. It also, with that blue dotted curve, you'll also notice there that it does start with a positive number. That's due to that initial velocity condition. Because the acceleration is negative, though, it starts positive but starts to decline because acceleration is negative. At some point, it goes down below 0, meaning that it's got now a negative velocity. And then what you'll notice here is that position starts at 0. Because we have that initial velocity, it starts to increase right at first, but then that position starts to decrease whenever the velocity changes direction, right? So anyway, figured I'd kind of go through those graphs and mention how the velocity, acceleration, and position happen for block A. Again, that's all stuff that we already did. We did it manually a few seconds ago, or with our last technique that we did manually. And so what we want to do now is move on and figure out what are the acceleration, velocity, and displacement for block B. Okay, here's how we're going to do that. Remember, the relationship that we had was negative 2/3, right? So we may as well just start with position. The position, I'll use r vector for that, r of b. This is going to be a function of t, right? And it's actually super easy. We just set it equal to negative 2/3 of, we've already defined our other position, a, as a function of t. And what's really nice about doing this in Mathcad is now that I've, that's all I really need to type. I type that much in, and if I want to see what's in there, I can use a symbolic evaluation tool, right? So within RB there, I can use this little arrow right here. It'll show me what that turns out to be as a function rather than just a straight result. You can also do a straight result. Remember, we're trying to evaluate all of these at 3 seconds. Okay, and again, remember, I've stripped my units off. So, I'm doing all of these with the presumed units of, up here at the beginning of this problem, we had things that were, let's see, in inches, right? So where I'm going to have this position here, this is a position in inches, or displacement in inches, I should say. All right. Well, one of the things that I was supposed to do is actually express this RB in vector form. How do you think I should do that? Okay, how about RB, okay, and I'll maybe put another subscript on there of x, so my x component of this vector. All right, and I'll tell you what I'll do as well. I add another variable in here. Now the variable happens to not be something that is truly variable, it's something that we know, but remember, it's going to add in this angle of 35 degrees that we had on the picture up there, okay? And so what I like to do there is, so that I can express it in terms of that angle, I'll put this as a function of both t and theta. All right, and it's actually super simple. All I got to do is take whatever my position was for b as a function of t, and multiply it by whatever trig function I need to make sure it's going the correct direction. This can be just a little bit tricky, and so I want to go back up and look at the picture again so that we get it correct. So first of all, you'll notice here, because it's measured relative to the horizontal and I'm trying to find the horizontal, then it's an adjacent component. So we can start with saying we know we need to use a cosine. All right. The next thing I need to do is think, I've already got a negative sign in there. The negative sign indicates that when block A is moving in the direction that RA gets larger, it means that RB is getting smaller. That's what the negative sign means in the negative 2/3, right? So what I want to do there is now look at if RB is positive, right? We kind of separate question. If RB is positive, then do I have, or it's actually probably easiest to think of it in terms of velocities. If the velocity of B is positive, does that represent a positive or negative component in the horizontal direction for that point B? Okay. And I would say, based on the direction we defined RB, we're saying it's positive going that way, right? Going up that way, it's positive, okay? And so because it's going positive up that way, for RB, that's actually a negative direction in the x. And so that motivates me to go down here and multiply this by negative cosine of theta. Okay, and if I want to evaluate that at the time that we're interested in, I can put in 3, meaning 3 seconds, and an angle of 35 degrees. Okay. what is this number that comes out of here? Negative 9.011. What does that mean? Okay. So here's what it means. Point A wound up at a position 16.5 inches lower than it started out, right? That implies, based on the negative 2/3 ratio, point B ends up 11 inches upward and to the left from where it started out, okay? And what we're doing here is we're just figuring out just the leftward component of that, and because it's going up and to the left is negative x, so that's the negative, and the 9.011 is that x component, okay? And again, if you want to show this as a, more as a function rather than as a, just a value, whoops, then you can use that symbolic evaluation operator. All right, what do you think we want to do for the y direction? It actually looks very similar to what I just did in the x direction, so as a starting point, let me just copy them. And in the y direction, let me just first of all name this with a y right here. And then next to that, I have RB times t, that's fine, times what do I need to do now for my trig function to get the vertical direction? Okay, well, when RB increases, then that actually leads to an increase in y, right? Because y moves upward and RB generally moves in the upward direction as far as the vertical part of it, right? So what I need to do for my trig function is use the sine function, and I don't need to negate it. So I'll just put in sine of theta. Okay, for these others, I just really just need to rename them. And that gives me those functions and those values that were requested as far as position is concerned for part B. All right. Actually, let me go ahead at this point and move on to part C for the question of displacement R, right? For the question of how far these things have moved. Part C of the question was, what is the displacement of B relative to A? All right, I'll just do that with this notation. It is, if I keep these two variables in place, it's going to be a function of t and theta. Okay, and I tell you what I'm going to do for this first one is just do the x direction. Okay, and if I want the position of B relative to A, then what I need to do is take my function for B and subtract my function for A. Okay, I don't have to go and copy and paste them though. I can just directly use them. So in the x direction, here is my function. This is the name of it. This is my function in the x direction for the position of B. Okay. And what's a function for the, I've been using the term position. I really mean displacement, right? So the term for the displacement of A, what's its value going to be? Well, let me ask you this. Based on the picture that we had up here, does block A move in the x direction at all? All right. I would say not. Here's where the reason I say not is that we have this weight that hangs down. This pulley over here is fixed in place. It's just staying there. Pulley C, there's no influences that make pulley C want to move anywhere but just straight up and down, right? And so the two ropes that hold A just move straight up and down. And so that part just moves straight up and down. And if it moves straight up and down, then it will have zero displacement in the x direction. And so where I go down here, I just put in 0 for my amount of displacement in the x direction for block A. And this difference between these two values gives me the displacement of B relative to A. And it's not super interesting because it will just turn out to be the exact same thing, at least for this one. It will turn out to be the exact same thing as, and this is supposed to be in the x, it'll turn out to be the exact same thing as, and I'm supposed to put in here 3 and 35 degrees. Same thing as what I had just for RBX. Okay, because I have a 0 for that other term. All right, so I know that it kind of belabors that point just a little bit, but I wanted to not skip that step. All right, it's important to identify that we have 0 displacement that will happen for block A, at least in the x direction. In the y direction, though, we have a different situation. What do you think I have in my y direction? Okay, for B relative to A, I'll look at my displacement of B and subtract my displacement of A. Okay, and I never did express that up higher in terms of it being the y component, but it's all in the y, right? So I can just put it in without any other notators, denotations. All right, so here I've got RB relative to A in the y, and I'm going to do that at 3 seconds and at an angle of 35 degrees. Okay, and that tells me that my y component of B relative to A has a difference basically of 22.809 inches. Okay, all of these values that I just came up with will be in inches. Okay, well, I can actually do these same type of things to figure out functions for these things. So like the function that I have here, I can determine what that is using a symbolic manipulation or symbolic evaluator. All right, and what it basically does is it puts together all the pieces. R of B relative to A in the y direction is the same type of thing for T and theta with a symbolic evaluator. And you'll see there, it doesn't really necessarily try to reduce it at all, but that is a valid function. There's some other neat things that you can do. If you would like, you can ask it to simplify this. All right, sometimes it comes up with a little bit better expression or more compact expression sometimes if you ask it to do that. All right. A couple other things I'll touch on here, even though this was basically all that I asked for with respect to the position side of things. An interesting thing is, what if you come up with the overall magnitude of the position or the displacement of B relative to A? How do you think you come up with that? I'll just call that RB relative to A without any other subscripts. Okay, and I'll tell you what, rather than do functions for this, I'll just evaluate it at our test case. Well, you do just a square root of the sum of the squares. So you do a square root of what I have here, all right, squared, but I probably need to change T to 3 and theta to 35 degrees and square this and add to it. Okay, the same idea, but with the y component instead of the x. All right, And what that gives me is how far have we moved one relative to the other as a result of the motion that has happened for this system. In other words, how far, if you're standing on block A, how much further away does block B look like it is now that we've moved through this motion? Okay, and that's a value for that. We can also determine, what direction it looked like it moved. All right, the direction it looked like it moved can be evaluated as an angle. Okay, I like to use this function. It's called arctangent 2. Right. Nice thing about arctangent 2, atan 2 here, is that you can put in your two arguments separately. You have your y component and your x component. Actually, I don't know why they did it this way, although it doesn't bother me too much, but you put in your x first is how this function is constructed within Mathcad. So you put in your x component first, then you put in your y component, and it'll then tell you what the position is of like where it looks like it was moving. And it does this as an angle between, well, basically between negative 180 and positive 180, right? So it looks, if you're standing on block A, it looks like the motion of block B moved such that it was off in an angle at 111.556 degrees relative to positive x measured counterclockwise. Okay, so those I didn't necessarily ask for in the problem, but I figured I'd go ahead and put them in there anyway in case those are things that you think are interesting. All right, let's move on and look at velocity. Okay, similar kind of deal, right? The velocity of B is equal to, do this as lowercase v. Velocity of B is equal to negative 2/3, based on our little calculation we did last time, times the velocity of A. And I guess I should have both of these as functions of t. All right, so we're moving on to the velocity question. The velocity then for B at 3 seconds is something we can find. All right, we can also do that symbolically if we want to get the function. Okay, and this is in the direction that B is moving. All right, so if I want to do this where I'm coming up with the velocity of B only in the x direction, I use the same technique that I did for position, and I just multiply what I had for my total velocity of B and multiply it by negative cosine of theta, which means if I want to leave that in terms of theta, I have to add another argument here of theta. Okay. So now the velocity of B in the x direction for 3 and 35 degrees is that. And the velocity of B, if I want to just do this symbolically, I can put it in terms of those symbols and evaluate it symbolically. At least in theory, I can't. I need that to be x. All right, and I can kind of do the same thing in the y. like so. All right. How do you think I end up with like b relative to a? I could do it in the x and y direction separately. So in the x direction, I basically find what my velocity was in the x direction, and I subtract what do you think? What did I do for the displacement question in the x direction? Remember, horizontally, block A is moving entirely vertically, right? So I can just subtract 0 because I don't have any motion in the x direction for block A. Okay. In the y direction, though, I will have two different components there. All right, and what I'll need to put in is my velocity of in the y direction for b, and subtract from it the velocity of a. Remember, a moves entirely in the y, right? So I didn't have any special notator on there that mentioned that it went entirely in the y. Okay. So, you know, again, we can do functions for these if we want. Simply by using a symbolic evaluation. The one that might be kind of interesting here is this one. Okay. And, you know, just like I did before, sometimes it helps if you try to ask it to simplify. That's also in the symbolic toolbar that you see there. All right, and for the last thing that I'll do here is let's just figure out what that velocity magnitude is, b relative to a, at this point in time that we're curious about. Okay. Something like this. All right, so the velocity of b relative to a is just 1.486, and that would be in units of inches per second. Right? Remember, we stripped all of our units off to make the calculus stuff and the some of our symbolic manipulations here work better, but that's what that the units of that would be in. Are you curious what the angle might end up being? Anyone have any theories? Okay. We'll just put in our x first. And then the y. Does that surprise anyone? we're saying here is that the angle for the velocity that I just calculated here, this is how fast it looks like block B is moving relative to A. We're saying that direction it looks like it's moving is the same as the direction it looks like there was a difference in position. All right? That makes sense, right? I mean, it does to me. It makes sense that there should be a similar direction for those two ideas. All right. I think we're going to call it good here. What would you do if you wanted to extend this onto acceleration? I gave you two examples, right? I did one for displacement where I had my R's. I did the exact same thing basically for V. What do you think we would have to do for acceleration? Just one more time. Only do it for accelerations instead of displacement or velocity. All right. So I think we're going to call it good on that problem. Any questions about it, either conceptual or something specific?